Hello everyone, and welcome to week 2 of our course. We have lecture 3 here that is going to start with the introduction to linear transformation. This is a fairly interesting topic and I think you are going to enjoy this. So let's begin, shall we? Well, it's not like you have any other option anyway. Okay, so we are going to start again from the very basic question of what exactly is a linear transformation. And again, I'm going to get rid of the word linear and just focus on the word transformation. When you think of the word transformation, what do you think of? Well, for me, when I think of transformation, I'm thinking of changing something into something else. So for example, we have an apple here, and if I transform it, it's going to be converted into something that is not an apple. So for example, in this case, I am applying the transformation called making juice, and my apple is transformed into a glass of apple juice. Nice, right? I'd like a glass of apple juice right now. Anyway, so if I apply the same transformation to one orange, I'm going to get a glass of orange juice. Now for consistency, let's assume that every unit of a fruit contains exactly 1 liter of juice. So 1 apple is going to be transformed into 1 liter of apple juice, and similarly 1 orange is going to get you 1 liter of orange juice. Now you can also think of this as mapping, because we have two sets here, the set of domain and codomain, and the transformation actually is mapping each element of the domain into some element of the codomain. So this is exactly like a function, and we write it as the transformation from the set of fruits to the set of juice. Now you might be wondering what is the difference between a transformation and a function, and to be honest with you, there is really not much difference. But why we are using the word transformation instead of function will be explained to some extent in the next lecture. Well, for now, let's bring back the word linear back into the mix. When does a transformation become a linear transformation? For a transformation to be considered a linear transformation, there has to be two rules satisfied. The first of which is this one. In here, the transformation is going from the set of u to the set of x. U and v are elements of set of u, and t of u and t of v and t of u plus v are elements of the set of x. Alright, so the rule says that if I transform a summation of two elements, the result has to match with what I would have got if I transform the individual elements first and then summed it up later. Alright, so let's see what it translates to in our example. We have an apple and an orange, both transformed into their respective glass of juice. So if I added these two together first, I'd get some weird mixture of two fruits, apples and oranges, and if I applied the transformation on that, I'd get a mixture of apple and orange juice, right? And as each fruit contains 1 liter of juice, this mixture here has 2 fruits in it, so the amount of juice is going to be 2 liter. Now instead of adding these two elements together first and then transforming it, what if I transformed the elements first and then added them together? Well, first transforming the apple and oranges gives me 2 glasses of apple juice and orange juice. If I mix them together, I get the same thing. I get 2 liters of juice, and the juice is a mixture of apple and orange. So this condition here, this transformation here, satisfies our first condition. Let's look at the second condition. The second condition says that if I transform a multiple, c is a scalar here, c is a real number. So if I transform a scalar multiple of some element, so the result has to match with what I would have got if I transformed the element first and then multiplied the result with the same factor. Again, to understand it better, let's see what it means in our example. We have an apple which is transformed into 1 liter of apple juice. What if I multiply this element by 3? I get 3 apples, right? What if I apply this transformation into this bunch here? I'm making juice, right? So I get apple juice, but as there are 3 of them, I get 3 liters of apple juice. Every fruit will give me 1 liter. Now, instead of multiplying them first and then transforming it, what if I transform the apple first, making the juice, and then multiplied it by 3? I get the same thing, because either way I'm getting 3 liters of apple juice. So this transformation here, this transformation of making juice, satisfies both the condition for a transformation to become a linear transformation. So this is our transformation, and this is approved to be a linear transformation. Now let's see an example where a transformation is in fact not a linear transformation. In this example, I'm not just making juice. My transformation tells me that after making juice, I will have to add exactly 1 ice cube to it, right? So if I transform 1 apple, I get 1 liter of apple juice and 1 ice cube. If I transform 3 apples, I get 3 liters of apple juice and 1 ice cube, because after making juice, I will add 1 ice cube. Doesn't matter how many apples there are. I'm transforming the whole thing, getting the 3 liters of apple juice, adding 1 ice cube later. But what if I transformed it first, getting this here, and then multiply it by 3? I'll get 3 apple cubes. This is not apple cubes, this is ice cubes. So this is not the same, which means this transformation right here is not a linear transformation. Pretty simple, right? So let's go back to the theory. This is our definition of a linear transformation. If a transformation follows these 2 rules, then we can say that the transformation is linear. And in fact, we can actually combine these 2 rules together into a single rule, and that is this one. Because in this single rule, we are combining the rule of scalar multiplication and addition together. Now, does this look familiar to you? Well, it should, because this is just a linear combination of u and v. And this part is a linear combination of t of u and t of v, which means that linear transformation has to maintain the linear combination relationships. Alright, so what that means is, if something is a linear combination of some other 2 things, let's say, if I take that transformation, it has to maintain the same linear combination relationship. It has to be t of x and b of t of y. I put an extra bracket here. Pardon me, please. Alright, so let's be serious for a moment and get rid of all the apples and oranges and see a valid example. We have a transformation that goes from r squared to r squared, which means a 2-dimensional vector will be transformed into some other 2-dimensional vector. And the definition of the transformation is the vector xy is going to be transformed into minus x minus y. So this is pretty simple. A vector, if the vector is 3 and 4, the result is going to be minus 3 and minus 4. So let's say this is our 2 vectors. If I transform the first one, I get minus x1 and minus y1. If I transform the second vector, I get the vector minus x2 and minus y2. Now, let's see if the 2 conditions are satisfied. If I add them together first, and then take the transformation of it, I get minus x1 minus x2 and minus y1 minus y2, this vector. And this is exactly the same as this. The summation of 2 vectors, one is going to be minus x1 minus y1 and the other is going to be minus x2 and minus y2. And these 2 vectors are just the transformation of the 2 original vectors. So the first condition is satisfied. Now about the second condition. If I multiply the vector with some scalar c and then take the transformation of it, what I get is this vector right here, and this is just the same as multiplying the minus x1 minus x2 vector with c, because we know that a scalar can be taken out of the matrix. And this is exactly the same as the same multiplication of the transformation itself. So the second condition is also satisfied. So we can say that this transformation here, right here, this is a valid linear transformation. Well, pretty straightforward, right? Before wrapping up, let's see another example where the definition of the transformation is actually not a linear definition. So the definition of this transformation here tells us that this transformation deals with 2-dimensional vectors and transforms them into some other 2-dimensional vectors. This is a transformation from r squared to r squared, and the definition of the transformation is it simply adds this vector, this special 1 minus 1 vector, to the original vector, and that is the result of the transformation. So let's say we have a vector 2, 3, and we are going to transform it. So if we really want to transform it, we are going to have to add this 1 minus 1 vector to it, and that gives us the transformation itself. So this is the result of the transformation of the vector 2, 3. Now if I scale it by a factor of 2, for example, I get this vector. Remember this point because this is where we landed in when we multiplied the transformation by a factor of 2. Now let's see, instead of multiplying the transformation itself, what would happen if I multiplied the vector first and then transformed it. So this is our vector, and I'm going to, instead of transforming it first, I'm going to first multiply it by a factor of 2 and then apply the transformation. And the transformation is just adding 1 minus 1 to this vector, which gets us to this point, right? And this point is not the same point as the one where we landed earlier. So obviously these two are not equal, and our second condition has been violated. So this cannot be a linear transformation. I hope that was pretty clear. If it wasn't, I guess you can watch the video again, right? Okay, so before finishing, let's just do a quick recap. Alright, so a transformation is like a function. It maps the element of one set, which is known as the domain, to some member of another set, which is known as the codomain, exactly like a function. And a transformation is going to be considered a linear transformation if it follows the two rules. The summation of two elements and then transforming it has to give the same result as transforming the elements first and then summing it. And the second condition, multiplying an element with a scalar number and then transforming it has to give us the same result as transforming the element first and then multiplying it by the same scaling factor. So if these conditions are met, we have our linear transformation. So that's pretty much it. Thank you for joining with us today, and in the next lecture we are going to talk about matrix transformation, which is the largest portion of linear transformation, and all the linear transformation we are going to see in this course, in this semester, are all going to be matrix transformation as well. So this is very important. I'm going to see you on that video. Thank you and take care.